Welcome back, and thank you very much for watching this lecture video. In this lecture, I will keep talking about the SN1, E1 chemical reactions, and I will try to go through effective solvent, living group, and also stereochemistry of SN1 chemical reactions. And the first one that we're going to go through, it will be the solvent. So as you see here, and as we increase the dielectric effect of the solvent, or the solvent, as the solvent gets more polar, rate of the reaction also goes up. We started from almost no chemical reaction to 40 times here to 40. So the reaction clearly is getting way faster than initial one. And I need to know why the polar solvent is going to make the system more is going to make the chemical reaction faster. Okay, let's go after the chemical reaction. The chemical reaction starts with creating an intermediate. The question is what will happen to the intermediate and also the living group after they are, after we lose the bond between them. So we get a carbocation, and this is our carbocation. So I can, for example, draw the carbocation like this. So say I have a carbon that attached to three groups. They can be anything, call them R. And now we have an orbital. That orbital is empty. And okay, it's a p orbital. There is a positive charge on this carbon. And also we have a chloride. And the chloride, it has four lone pairs. If you have a polar solvent, like say, for example, water, it has lone pairs, and also it has hydrogen attached to a polar element, electronegative element. So hydrogen is going to have a positive charge, while oxygen has a negative charge. Okay. Now, when it comes to the carbocation, we are missing electron. So very soon, oxygen, it will be pointing to the carbocation, and it will try to have interaction with it. So we can have interaction with the p orbital, and remember that's a p orbital, and that's gonna make the system stable. Okay, and or you can also say this, those R groups are gonna give electron to carbon, and if they give electron to carbon, they're gonna have a positive charge. So how about this? Oxygen also can reach the R groups and have interaction with them, and try to neutralize the positive charge, the partial positive charge that right now we have on our groups. So solvent can stabilize the intermediate. I'm talking about the carbocation, and anything that stabilizes the carbocation, it will drop the activation energy. That means the reaction will be faster. Okay, so the reaction will be faster if carbocation gets stable. Now let's talk about the living group. This is the living group. Living group, it has a negative charge, so it's -1 technically right now. And because it has negative charge, that means it has extra charge. We need to stabilize it. And in this case, oxygen is going to put the water molecule. It will put the hydrogen facing or pointing to the chlorine. And if that won't happen, in that case, I'm going to say each hydrogen, it has a positive charge, a partial positive charge. Those hydrogens, they can have interaction with the lone pairs and make chloride stable, or reduce the negative charge on the chloride. Okay, again, we have interaction here. So water molecule or polar solvent can stabilize both the intermediate and the living group. If that's the case, then I'm going to say this reaction, or the dissociation reaction, is going to happen faster. And that's the reason polar solvent will stabilize, will actually speed up of SN1 or E1 chemical reaction. And how about, so how come when we were talking about SN2, we said opposite of it is going to be the case? For SN2, you need to have a protic solvent. Okay, you need to have a protic solvent. Well, like if you use a protic solvent, okay, the rate of the reaction it will be slower. And when we are talking about SN1, we need to have a protic solvent, and protic solvent will make the reaction technically faster. Okay, I'm talking about protic. A protic solvent is the solvent that has acidic H. A protic does not have. Okay, so be careful about those two. Okay, let me highlight this one. Okay, now you need to ask yourself, where is this, where the solvent is going to affect, like the rate of the reaction, and or how it's going to affect it. And based on the graph that I see, the transition state, okay, transition state is the one that's going to get affected. Let's see. So this is the activation energy. And activation energy here went down. Okay. This is going to be the activation energy. Well, it used to be this number. Used to be that number. So clearly activation energy went down. Okay, now let's zoom on that. Let's see why activation energy for SN2 it will go up. It will go up if you use polar protic solvent. Okay, it has to do with the transition state. This is the transition state for our SN2 reaction. You will have groups there, 3 groups there, and one here. This one will be completely planar. Now I have a group nucleophile that is coming. Nucleophile, it can have a negative charge or a lone pair, and trying to share it with carbon. Well, the leaving group at the same time is taking the electrons, 2 electrons, and it's leaving. Okay, so the nucleophile, it has a negative charge or partial negative charge. Leaving group is taking the electrons with it. It's taking those 2 electrons and it will leave. So this one also, it will have negative charge. Okay, the question is, where is the positive charge? The positive charge is sitting on this carbon. The positive charge is hidden on carbon. Okay, now, well, when I look to the carbon-cation, we have an intermediate carbon, okay, that it has 3 groups, say R1, R2, and then we have here another R, and now we have an empty orbital here. Okay, and so now I have an empty orbital, and as you see, this one is a completely planar. I can attach, I can connect those 2, and if I connect them, I will get a plane. And I have a p orbital up and down, and right, left side of the carbon-cation. Okay. Now, can we reach that orbital, the empty orbital, from right or left? Yes, we can easily reach it. So your solvent, if it's, for example, water, can easily reach this side of the empty orbital, or it can reach it actually from other side. So how about this? We say the intermediate, the carbon-cation in this case, is kind of like naked. And like the nucleophile does not see any technically steric effect here to reach it. And because it's a flat, it can easily reach it. Yes, sometimes maybe one side is more crowded than another side. It can happen. But overall, the positive charge is open, is open to the solvent, and solvent can easily detect it. Well, with SN2 that wasn't the case. So with the SN1, we need to have a polar protic solvent. So we need to be polar and protic. Okay, polar and protic to stabilize the intermediate. Also, we are getting like a leaving group. A leaving group, it has a negative charge. So not only the intermediate, we are stabilizing the leaving group as well. Okay, and with SN2, now SN2, we don't have a positive charge. We have a partial positive charge, and it's located or buried on carbon. Okay, now let's talk about the nucleophile. Okay, nucleophile. How about the nucleophile by itself? Okay, with the SN2 reaction, we say K multiply the concentration of the nucleophile multiply the substrate. And each one to the first. Now, if your nucleophile, for example, something like OH, that OH will be stabilized. Okay. Will be stabilized highly by solvent, by protic solvent, like, say, water. Okay, what does it mean? More stable. Okay, more stable means less reactive. Okay, more stable, less reactive. So if you use a polar solvent, you're going to kill the nucleophile. Your nucleophile is not going to be that stable, and this is going to be really bad for SN2 reaction. So for SN2 reaction, when it comes to nucleophile, you need to have a protic solvent. A solvent that cannot stabilize, the nucleophile. And yes, because you don't have much positive charge, you don't care about the intermediate. Well, when it comes to SN1 or E1, we say the first step of the chemical reaction is this: creating a carbocation. And the rate of the reaction, we write it this way. We say K multiply concentration of the substrate. Now, where is the nucleophile? Nucleophile will be added in a step that is going to be way faster than the first step. This one is the rate determining step. That means it's slow. Okay, so we're going to have another step, and that step, nucleophile will be added. So you are adding a nucleophile at a step that is already fast. And because it's fast, if you use a polar solvent, who cares? The polar solvent is not gonna drop rate of reaction that down. So then it will be the rate determining the second step. It will be rate determining step. No, under any condition, first step it will be always the rate determining step. Why? Because you are breaking a chemical bond versus pairing two groups to each other. So under any condition, first step it will be the slowest step, not the second step. And because I'm adding the nucleophile in a faster step, polar solvent, polar protic solvent, okay, will not drop the rate of the reaction. Okay, will not drop the rate. Okay, that's not gonna happen. Okay, rate of reaction, it will not go down. Why? Because again, because you are adding in a step that is fast enough. Okay, and this is the main difference between SN2 reaction and SN1 in the polar versus the polar protic versus polar protic solvent. And I'm going to stop the lecture here, and thank you very much.